Well, I'd like to welcome everybody to the undergraduate research seminar and our session today, which is on time and space continuum. And we have 3 excellent talks ready for you to listen to and to hear. And we're going to start off with third-year physics major, Rachel Herr. Rachel is a fellow Michigander, I guess in part. You sound like you moved around a little, Rachel. Describes herself as a non-traditional student and said that she wanted to initially learn and apply an understanding of how human bodies and living things work. But when she started taking physics classes, she found herself asking questions that probed at the deeper mechanisms and underlying physical nature that inform chemical and biological processes. The title of Rachel's talk is Inferring Binary Black Hole Merger Properties from Contaminated Gravitational Wave Signals. I'd like to say that just a decade ago, the notion of actually detecting gravitational waves would have elicited smiles and polite laughter. But as of now, we not only can detect gravitational waves using the LIGO facility, among others, but members of the Ben Fry group are even now looking for contaminated gravity waves. So I'd like to hand off to Rachel, and please, and welcome, Rachel. We look forward to your talk.
Awesome. Thanks for the introduction, Dean. I'm gonna go ahead and share my screen.
Well, before you start, Rachel, I just wanted to say, please feel free to enter questions as they arise when you listen to the talks. We will have a little time after each talk to answer questions specific to that talk. And then hopefully at the end of this session, we'll have time to answer any other questions that might arise. Rachel, please.
Awesome. Thank you, Dean. I just want to make sure that we can see my slides okay?
Yes.
Great. Thanks. Hi, everyone. Thank you for attending. And thanks, Dean, again for the introduction. Today, I'm here to talk about how we detect gravitational waves emitted by compact binary systems, such as the 2 orbiting black holes that we see in this photo. Specifically, I've been investigating a possible algorithm for more robustly extracting the physical properties of these systems if the gravitational wave signal has been contaminated by an instrumental glitch. That's a lot to take in, and I'll come back to many of the details later. But the main focus of my research is more or less asking the question, how can we improve the accuracy of our analyses when a burst of noise from the detectors coincides with an astrophysical signal? I also wanted to take a moment to describe the photo in the background. This is a snapshot of a computer simulation, not an actual photo, unfortunately, of 2 black holes caught in each other's orbit, i.e. a binary black hole system. For those that aren't familiar, black holes are a region in space in which gravity is so strong that nothing can escape it, including light itself. This makes it the densest object in the universe, and that's why we see the light bent around these black holes being bent the way that they are. So these simulations look really cool, but why are we interested in gravitational waves? For me, I was attracted to the fact that it challenged my idea of something that felt very intimate to my existence. It challenged my notion of the very nature of the physical structure in which we live and function. We mostly assume space to be the sort of static nature that's unchanged throughout the universe, but that's not really true. Einstein's theory of relativity predicted black holes and gravitational waves over 100 years ago, and only about 6 years ago were we able to make the first ever direct detection of gravitational waves, as well as the first detection ever of a binary black hole system. For the sake of time, I won't go through all the reasons, but I've put a few on the slide, and we'll just mention that gravitational wave astronomy has opened up a whole new world for astronomical observation. It's allowed us to probe areas in astrophysics, offer unique tests in general relativity, offer cosmology and independent measurement of the expansion rate of the universe, and also allows us to probe existence of some exotic objects like quark or boson stars and put constraints on objects like cosmic strings. So there's a lot of info to be gathered from these gravitational waves, which begs the question, what exactly are gravitational waves and what is spacetime? Simply put, spacetime is a mathematical object which fuses 3D space with one-dimensional time. And this figure on the right is a 3D analogy to spacetime, and we can see that the mass bends spacetime towards it wherever it moves. This is relevant for gravitational waves because this is spacetime is the medium through which those gravitational waves propagate. Meanwhile, these gravitational waves themselves are propagating waves of energy which distort spacetime as they move through it. And in the figure on the left, you can see a compact binary system, specifically a binary black hole system, orbiting around one another. And you can see that as they spiral inwards, the frequency of the gravitational waves emitted increases, as well as the amplitude of the waves. So there's more and more energy being radiated as they come in closer together. So now that we have some of the theory, how do we actually detect these waves? Our main instrument are gravitational wave observatories or detectors. We have the LIGO network, which is made up of 2 detectors here in the US. Virgo has one in Italy, and there are 2 being constructed at the moment, Kagra in Japan and Indigo in India. The way that these detectors work can be sort of parsed out from the diagram on the right, the schematic. We essentially have 2 perfectly perpendicular arms of the detector. And for LIGO detectors, they're actually 4 kilometers long. And we shoot a laser down at point 1 towards point 2. And at point 2, there's a beam splitter which directs the waves across each arm in such a way that the waves that are propagated are out of phase with one another, so that when they hit the mirrors and bounce back, they perfectly deconstruct. And at point 5, where the actual light detector is, if there's no gravitational wave present, then we should see nothing there. If there is a gravitational wave present, then the arms actually, because of the space-time distortion, are affected differentially, and one arm will contract and the other arm will lengthen. And that will cause the perfect deconstructive wave to essentially be constructive, and we'll see some light at point 5. So beyond just the detectors, it's also the international collaboration of over 1,000 scientists that help make this instrument and experimentation possible. And I also think it's important to note that the differential length of the arms moves on the scale of 1/10,000th the width of a proton, which is about 10 to the negative 19 meters, which is the smallest measurement that humans have made to date. This is a diagram of sort of the breadth of binary black hole systems and a couple neutron star systems that we've detected to date. So far, we've detected 50. And on the y-axis, you can see this describes the mass of the black holes in terms of solar mass. So they all lie around 5 to 160 solar masses. And we can see in the figure in the bottom right too, that as we move forward and as detectors are being updated, we're seeing more and more gravitational wave events, which is great. So now that we've covered some of the theory of how we detect gravitational waves, now the question remains, how can we know that the gravitational wave signal, for example, how can we know that from the gravitational wave signal that, for example, these are the masses or that they're this distance away in the sky? How do we make that connection? So first we say, okay, the model is after transforming the time domain data into the frequency domain, we assume that the data is composed of the signal and the Gaussian noise. The signal models are informed by general relativity, post-Newtonian approximations, and some other theory that I won't go into detail with. Now we can use this model in terms of Bayes' rule. And just for some intuition, I'll give an example for this. Let's say, for example, that you're in the university and you hear a fire alarm go off. What's the probability that there's actually a fire, given the fact that the fire alarm just went off? H, your hypothesis is that there is a fire, and E, your evidence is the fact that the fire alarm just went off. According to Bayes' rule, we can find this probability, called the posterior, by taking into account the prior belief, which is your belief in terms of probability that there's a fire before you hear the fire alarm go off. So it's your prior belief. And then there's the likelihood, which is the likelihood of the fire alarm going off in the case that there actually is a fire, which hopefully is pretty high. In terms of probability distributions, we can see in the figure on the right that the prior distribution times the likelihood gives us this new distribution, which is our posterior that we're looking for. Bayesian inference, sort of the crux of gravitational wave data analysis, is essentially Bayes' rule, but iteratively applying it as evidence comes in. Specifically in gravitational wave analysis, there are actually 15 parameters that we need to describe a binary black hole system. So in the second equation, H has become a vector of parameters, theta, while D, the data, replaces the evidence. And the one variable distribution in the figure on the right turns into a higher dimensional parameter space or probability space, which the visualization for kind of breaks down beyond 2 dimensions. In order to perform parameter estimation, we apply computational sampling methods. So after we've, based off of theory, defined our prior beliefs and our formula for our likelihood, we can calculate the first iteration of the posterior, then draw a random point in parameter space from that posterior distribution. We then propose a jump to another point in parameter space and then calculate its posterior. If it's higher, we accept the jump and continue the process iteratively. And if it's lower, we accept it based on some optimal condition given by the algorithm. This allows us to approximate the posterior distributions, given that mathematically we should converge asymptotically to the true posterior as long as we meet some convergence conditions. So the last few bits of that were a little bit more in the weeds, but essentially what we can move forward with is that we can use Bayes' theorem to update the probability distributions given our prior belief on what, for example, the mass of our black holes are, and then the sampling algorithms help us mathematically optimize exploration of this parameter space so that we can find our parameters and their uncertainties. So far, this has all been assuming that there's only Gaussian distributed noise. However, that's not always the case. So thermal noise, seismic noise, like anthropogenic noise coming from traffic or earth trembles. There's also quantum noise. These all do contribute to the Gaussian noise, but there's also instrumental glitches, which is what my research focuses on. Specifically, it focuses on how to handle data when an instrumental glitch arises at the same time as an astrophysical signal. And instrumental glitches are really just a general name for short bursts of noise whose source we don't necessarily know, but assume come from the detector itself. And funnily enough, these glitches can look like astrophysical signals in the data. In case you're curious, this is the frequency time domain graphs, which are the actual waveforms of a gravitational wave signal that's come in. And that color you see above the wave represents the power. Some members of the collaboration have created a sound clip for what these signals would sound like if we could hear them. And I'll just go ahead and play that for you now. Hopefully you can hear it. So part of the reason why I wanted to show this as well is because if we look at what the glitches look like in the data, you can see in the bottom right graph that the glitch exhibits a similar form to that of the merger phase of the signal. So right when it kind of chirps up. So it not only has the capacity to raise false detection flags, but also if it were to coincide at the same time as an incoming astrophysical signal, it contaminates our signal and our signal plus Gaussian noise model no longer works. These glitches occur up to 100 times per day in a single detector, and they occur in all of our detectors. And about 20% of gravitational wave events have required glitch removal before performing parameter estimation. Unfortunately, because the source of many glitches are unknown, modeling is a little bit non-trivial. However, sorry, 1 second, I think I lost my notes. Okay. Yeah, so previous studies show that we can actually model most of these glitches as the sum of sine Gaussian wavelets, and you can see in the diagram on the right, sinusoidal modulated by a Gaussian envelope. Currently, what we do to deal with these glitches is we subtract a point estimate of the glitch from the data and then perform parameter estimation to extract the masses, locations in the sky, and other parameters. However, there exists uncertainty in our glitch estimate, and that's not being propagated through the workflow currently when we just make a point estimate. Furthermore, there are also degeneracies that could exist between the signal and glitch model that we aren't accounting for. This means that there could be essentially different configurations of signal plus glitch results that aren't informing our final analysis. And this is the focus of my research, to find a way to address these degeneracies and allow for a way to propagate uncertainty so that we can perform a more robust parameter inference when there's a glitch present. This will help improve precision when getting out all of these interesting insights from gravitational wave analyses that I mentioned before. So my glitch model is pretty much the same as the previous glitch model in that we model the data to be the signal model plus Gaussian noise, but this time plus the glitch. The glitches are still modeled as a sum of a free number of sine Gaussian wavelets, but this is a little bit complicated to sample from since this gives us a multi-dimensional parameter space, or not a multi-dimensional, a changing dimensional parameter space since the number of wavelets is free to change. In order to deal with that, I apply the Dirichlet process prior on the weights of each wavelet, which I'll talk about in the next slide, but essentially it allows us to sort of mathematically, elegantly handle the free number of wavelets such that we can use a sampler which samples in continuous space and not discrete space, which tends to be a bit faster. I use the Hamiltonian Monte Carlo, specifically the no U-turn sampler extension of the Hamiltonian Monte Carlo. And here I've just, in the bottom right, I've shown the sine Gaussian wavelet in mathematical form with in trigonometric form and the parameters that we sample from, where K is the number of wavelets. So amplitude is attributed to all wavelets, and then each individual wavelet has its own frequency, central time, Q factor, phase shift, and weight actually isn't one of the sampling parameters, but it's the one that's most important. So now I'm going to talk a little bit about the Dirichlet process and then the no U-turn sampler, and then go over the results. The Dirichlet process is a little bit weird in the sense that it doesn't generate random values, but rather probability distributions themselves. However, we can avoid talking about that because the stick-breaking interpretation actually is much more intuitive than the original mathematical formalism, but it's entirely equivalent. The main nicety of using this prior on weights is that it determines the number of wavelet components for us while keeping the sampling space continuous. For those who are interested, the mathematical construction of the weights is in the bottom left there. And in the top right, we can see, for example, the line in black is we can imagine this as a unit stick. And according to our algorithm, we break off a particular weight, pi sub 1, which is the weight of the first wavelet. And then pi sub 2 is another weight component that we break off, and then that is distributed to the second component, and so on and so forth. So we can kind of see where the stick breaking name comes from. And you can also notice that as we break off more and more sticks, we get closer and closer to having 0 sticks left, or 0 part of this original stick left, which is where the truncated aspect of the stick breaking interpretation comes in. We're essentially saying that as the number of wavelets increases, the number of components increases, then we'll asymptotically reach 1, and we can do that sooner depending on our choice of alpha. Finally, the last part of my model is using the no U-turn sampler. This is, again, an extension of the Hamiltonian Monte Carlo, which augments the parameter space that we were talking about before, but we augment it with momentum so that instead of using sort of the random walk procedure that a lot of classic samplers use, we can make informed trajectories through parameter space, and that's through using Hamiltonian dynamics, hence the name. So for example, we can imagine like a 2-dimensional Gaussian distribution, like in the top right, and then turn that Gaussian distribution upside down. So it's kind of like a bowl, where the depth of the bowl is related to the darkness of the color in the figure. And we can pick a point in that space, imbue it with some momentum in some direction determined by the algorithm, and basically flick it with that and give it that momentum. And it'll traject parameter space, and this ends up being just way more efficient than classic random walk samplers. And you can see in the bottom right figure that when the posterior distribution, when the distribution that you're looking for has multiple modes, it gets a little bit more complex. So also, I use PyMC3 and Tensor. I've experimented with PyMC3 and TensorFlow for implementing this. And I just want to briefly touch back on my glitch model. So so we model the data as signal model plus Gaussian noise plus the glitch. We have a sum of a free number of assigned Gaussian wavelets. We have the Dirichlet process prior on the wavelet weights. We use the no U-turn sampler, and then we have broad priors on the rest of our parameters. So to clarify some of the preliminary results, the sampling was actually initially incoherent when I first coded up my model. It turns out that the nuts implementation in PyMC3 and TensorFlow only adapted the diagonals of what's called the mass matrix, which is basically a matrix that informs how we pick our random momentums and is related to the covariance. But fortunately, I found a PyMC dependent tool, PyMC3 dependent tool, Exoplanet, which had a full mass matrix adaptation scheme. Another issue we ran into was that the posterior ended up being degenerate or multimodal, kind of like what we saw in this bottom graph here. And that's due to what's called label switching, or a likelihood invariance. So the likelihood is essentially perfectly symmetrical. And what that means for us is that the sampler will initially characterize one wavelet and call it the second component, while characterizing another wavelet and calling it the fourth component. And during sampling, these labels of second and fourth can switch, even though the sort of what we're interested in remains the same. There are these two wavelets with these particular characteristics. to attack that, I dug into the guts of PyMC3 and implemented a swap step into the sampler to address the multimodal posterior. So what we do is we swap the central frequency, the sort of the Dirichlet version of the weights, and the other wavelet-specific parameters at particular fractions of the time during sampling. So like every 10 iterations, we propose this swap. Just for the sake of time, I'm going to skip some of this, but finally to leave off, right now where we're at is we're finding that the amplitude parameter actually really complicates the geometry of the posterior. The Dirichlet process weights are usually used in mixture models where the base function is actually a probability distribution itself. So incorporating this amplitude scaling parameter has been complicating inference. So right now we're planning to try to analytically marginalize over the amplitude so we don't have to worry about that complication in the posterior geometry. One thing that's cool about this project is that the sampling method could go beyond gravitational wave analyses. It could be useful for the statistical world in performing non-parametric regression. Also, if we succeed at developing this tool, we can propagate uncertainties in the glitch estimate to our parameter estimations while also accounting for degeneracies between the glitch model and signal. And again, this label switching or likelihood invariance is an open topic in what's called non-parametric methods in statistical analyses. So this could be useful outside of gravitational waves. That concludes the end of my talk. I wanted to say thanks to Ben Farr, my research advisor, other members of the research group who have helped me along the way, the entire LIGO collaboration for developing this experiment and continuing it, as well as the UO VPRI Fellowship for helping fund this research. Thank you, everyone.
Thank you, Rachel. So we have time for maybe about 5 minutes for questions. Does anybody have any questions? If so, I think you can type them into the Q&A and I will field them from there. Anyone have any questions for Rachel? I guess I'll start. I was noticing in your noise, your glitch waveform, that you were talking about it having essentially a Gaussian modulation of cosines and sines. And I wasn't clear how you actually estimate the frequencies of those cosines and sines. Is that a Monte Carlo kind of method where you just generate different frequencies and try to fit and see what happens?
Yeah, that's exactly what it is. Hamiltonian Monte Carlo is a version of the Markov chain Monte Carlo methods. Yeah, exactly.
Okay. Anyone else have any questions for Rachel? All right, well, if you do have some questions, when you're pondering her talk, you can enter them into the Q&A, and then hopefully at the end of this session, we'll have time to answer questions that pop up then. Not hearing any questions now, I'm going to go ahead and move into our second talk by Noah Kruss. Noah's a junior majoring in both physics and computer science. He's from Lake Oswego, Oregon. And here's my little promo. As standing waves, not to be confused with sitting or supine waves, are the basis for many, many physical phenomena, from the creation of music to the production of microwaves that heat up your coffee or cook your popcorn for you. Noah's going to tell us about a condition that impacts the formation of standing waves in peculiar ways in a talk that's entitled Evading Instabilities in Spring Mass Chains with Time-Modulated Stiffness. Take it away, Noah.
Okay, thank you, Dean. Let's see if I can get my screen sharing working. Okay. Can everyone see my presentation? Awesome. Sorry, I just want to move all of the Zoom stuff around so I can actually see my slides, which is usually a bit ideal. Okay, so I'm going to start. Hello, my name's Noah Kruss. I work for the Palos Group at the University of Oregon, and welcome to my presentation, Inferring Instabilities in Spring Mass Chains with Time-Modulated Stiffnesses. So to start off, let's talk about everyone's favorite intro-level physics problem, the spring mass chain. As I'm sure all of you have experienced, you're taking the intro-level physics class, and the teacher gets to the oscillation section of the textbook. They then go into a riveting derivation about how the physics of this system can be modeled using basic sinusoidal functions. In short, this is what my area of research is, just springs and masses moving back and forth in one dimension. Super simple, right? Well, maybe not super simple. You see, specifically what I research is what happens when you replace the springs with dynamic springs. By dynamic springs, I mean springs whose stiffnesses vary sinusoidally in time, according to this dynamic spring equation shown here. In this equation, K naught is the base stiffness of the springs, delta K is the oscillation amplitude, and omega is the oscillation frequency. So you're now probably asking yourself, why exactly would we want to add this extra level of complexity to a system such as this? Well, the answer to that question is that by adding time-modulated dynamics to systems, you're able to introduce some interesting physical phenomena. Two of the main phenomena that can be introduced are the breaking of time reversal symmetry and the addition of parametric amplification. So time reversal symmetry is the idea that if you reverse the flow of time in a system, the physics will be the same. So it's like the idea of if you have a sine wave propagating forward, you can't tell just by looking at the wave moving forward if you're going forward or backwards in time. So an example of breaking time reversal symmetry in a mechanical system can be seen in the setup shown in this figure. So in this figure, we have ring magnets lying along a rail housed by grounded solenoids. And by fluctuating the current passing through the solenoids, this system gains equivalent physics to that of a dynamical spring mass chain, where the magnets act as the particle masses and the magnetic force between the magnets act as the dynamic springs. And so if a signal is sent from the left to right end of the system, we can see in this plot here that the system, the physics is not the same as if the signal was sent right to left. Whatever the opposite is, I'm always terrified I just reversed it. But this can be seen specifically at this mill at like 19.6 hertz. So now let's talk about parametric amplification. So for a regular harmonic oscillating system, you can add energy to the system indefinitely by pulsing it as resonant frequency. In short, what parametric amplification is it's a method of adding energy to the system through oscillating the parameters that make up the system. So in this figure here, in this top part, we can see a basic spring mass system with a static spring. And so when the system is left to just oscillate due to gravity, we can see it goes through regular harmonic motion. However, if the spring is replaced with a dynamic spring, this system gains energy exponentially in time, quickly becoming unstable. So now, what exactly was the question that guided my research? Well, it's known that by adding time-modulated dynamics to a system, you run the risk of inserting instabilities due to the addition of parametric amplification. Thus, I set off to answer the question of, is there a way to reliably evade these instabilities? To do this, I needed to start off with creating a system that possessed time-modulated dynamics. To do this, I made use of the molecular dynamic package HUMD. And using HUMD, I set up a 1D chain of 36 particles with the two end particles pinned in place. I then went through the chain and offset all the particles from their equilibrium positions to initialize a 1D standing wave within the chain. And then I went through the system again and replaced all the springs with dynamic springs. So now, as already stated, the tricky thing about dynamical systems is that they're not always stable. And this instability appeared in my simulations when I allowed my system to be run over time. And so what these displacement versus time plots show are the position of a particle within my spring mass chain over the course of a simulation run. And so the only difference between the two simulations that these plots were created for was the arbitrary particle I decided to plot and the wavelength of the standing wave used to initialize the system. And so in these subplots here, we can see 2D representations of the standing waves used to create both or initialize both systems. And we can see that the parameter P I used to define my standing wave has an inverse relationship to the wavelength. So going back to these displacement versus time plots, it can be seen that the wavelength of the standing wave appears to affect whether or not my system goes through stable or unstable motion. In this left plot, we can see a stable condition where the system goes through relatively harmonic motion in time. Meanwhile, in this right plot, we can see an unstable condition where it gains energy exponentially in time. And if a real system was created using the parameters that used to define the simulation that made the right plot, the system would quickly spiral out of control. So to discover the physics of my system and determine a way to evade the instabilities, I needed to come up with a mathematical equation to model the physics of my system. Through some research, I discovered that the Mathieu function could be a possible equation to model my system. So Mathieu function is a second-order differential equation with a general form as shown here. And the Mathieu function possesses two independent types of solutions. So with this theory that the Mathieu function could model my system, the next thing I needed to do was determine equations to relate the parameters that make up my system to those of the general Mathieu function, specifically these A, Q, and Z terms. So through some more research, I was able to derive the following relations. As you can see, there's a lot to unpack here. So for the interest of time, I'm just going to go over the key highlights. The first thing to note is that the Z term of the general Mathieu function turns out to be dependent on the frequency of oscillation of my dynamical springs. Next, the Q term of the Mathieu function is equivalent to the A term times a gamma value. The gamma value is a measure of the strength of modulation of the dynamic springs, while the A value is proportional to the inverse wavelength squared. So with these relations, I was able to pick run parameters, thus that my system was stable. In this left plot, we can see a theoretical plot of a Mathieu function with Q and A values as shown here. In this right plot, we have another position versus time of a particle within my system over the course of a simulation run. And this run had run parameters that, when put through the relations I derived, produced a Q and A value as shown here. So as you can see, I was able to get a near identical match between the physics of my system and that of the Mathieu function using an A value that was roughly 6% larger than the one I theorized I needed. However, when I reran my simulations at a smaller wavelength, the match between the theoretical and actual values of A became nearly exact. So going back to the question that guided my research, I was looking to determine a way to reliably evade the instabilities that appear in my system. Since I was able to connect the physics of my system to the Mathieu function, this problem became one of ensuring that the Mathieu function was stable. So to do this, I needed to study a Mathieu stability chart. So what this chart shows is the even and odd solutions of the Mathieu function as a function of Q. And specifically what this chart tells us is that if the Mathieu function has run parameters that produce a point Q comma A that lies within one of these unshaded regions to the left of the solution lines, then the system should be stable. Meanwhile, if the point lies in one of the shaded regions to the right of the solution lines, the system will be unstable. So in short, by carefully selecting run parameters, thus that all standing waves lie in stable regions of this Mathieu stability chart, all instabilities within my system can be eliminated. So armed with this knowledge, controlling the instabilities becomes possible. This is really cool for multiple reasons. However, one of the reasons I find most interesting is this could theoretically allow us to use parametric amplification to counteract natural damping in systems. So this is what I've been doing over the course of the past term. And so specifically what I've been doing is I've used the relations I've derived to design a complex Gaussian wave packet that should theoretically be stable when parametrically amplified by adding time-modulated dynamics to the system through the dynamic springs with a set dk value. And so what I've done is I've initialized that packet in a 1D in a 1D line. And then I've let my simulations run in a system that possesses non-zero damping. And so we can see in this waterfall plot, as the simulations progress, the wave packet moves through the lines, but its amplitude is preserved. And so the wave packet, while moving, is preserved in time, despite the fact that this system possesses non-zero damping. So in short, this is telling us that the parametric amplification is adding energy back into the system, equivalent to the amount that the damping is removing from the system. Additionally, by performing Fourier transforms at various time steps and comparing back to the initial condition of the wave packet, it can be seen that the frequency information that makes up the packet is also being preserved in time. So this gives us both qualitative and quantitative evidence that parametric amplification can be used to counteract non-zero damping. Thank you. Does anyone have any questions?
Thank you, Noah. Does anyone have any questions? Please enter them into the Q&A. I guess you got me. I'll jump in. You got me curious here. I was looking up some information about shock absorbers. Since you're basically manipulating actively the stiffness of the spring, is that similar to what they do with shock absorbers in cars? You know? Seems like it might be.
To be honest, I have absolutely no idea. But I mean, I would think shock absorbers are just kind of regular springs that absorb the energy. As far as I know, actually creating dynamical springs in a real system hasn't been created yet. Mm-hmm. One of the closest things that I found was that ring mass system for modeling. And there was another system I came across that I think used harmonics or something. It was a harmonical system. Or sorry, I don't remember. I read came across a paper on it 2 terms ago, and I can't remember exactly what it said.
Does anyone else have any other questions for Noah about his talk? Everybody seems to be quiet, so the same thing applies. If you think of a question, please do enter it into the Q&A, and we'll try to get back to it in a bit. And in the meantime, I'm going to introduce our last speaker, Nicole Wales. And Nicole is both a physics and a chemistry major. She's a senior. Oh, she has a math minor. She's from Coos Bay, Oregon. She says that initially she wanted to be a pharmacist, but she took the introductory physics sequence as part of her biochemistry major and just got really interested in physics. She's participated in the NASA Community or Aerospace Scholars Program, and also she's done some research on perovskite solar cells, which is kind of interesting. I'd like to talk to her about that some other time, maybe offline. But today she's going to be talking about jamming. So when I play music, I like to think I'm jamming, but I'm guessing that my audience doesn't really find that to be true. But Nicole runs experiments that simulate the jamming of glass particles while undergoing random perturbations. And her talk is titled today, Correlations Between Neighboring Minima and Jamming. Nicole, please take it away.
Hello. All right, let me just share my screen here. Okay. All right. Can everybody see my screen? We good? Yeah. Okay. Okay. So, yeah. Hello. My name is Nicole Wales. Thank you for that introduction, by the way. So I'm in the Corwin lab at the U of O's physics department. We study glass because it is molecularly disordered like water, but rigid like a crystal. And while you can blow glass, you can't blow ice, and scientists don't actually understand why. So we eventually want to understand the glass transition, which is related to jamming, a phenomenon that I've been studying. Right. Oh, sorry, one second. There we go. Okay. So specifically, I've been looking at 3D jammed athermal simulated particle systems. Athermal just means zero temperature, which is a useful way to understand a system's behavior as a result of its geometry without the influence of temperature. And when you think of a jammed particle system, just imagine cramming so many marbles into a box that when you shake it, you don't hear them rolling around. So the replica theory of glasses has demonstrated that in the mean field limit of infinite dimensions, amorphous systems can exist in the marginal Gardner phase, of which jamming has been predicted to lie within. And just as a quick reminder, mean field theory just refers to the replacement of many individual interactions with a particle with a single average interaction with that particle. So jamming is predicted to lie within the Gardner phase, which is thought to resemble a solid that continually breaks and reforms cages, kind of like the purple particles we have here. Now, in my project, I'll be comparing the configurations of nearby energy wells of the energy landscape of simulated particle systems at jamming. And just to be clear, an energy landscape is a map that associates all the configurations of a given system to different energies. So energy wells, which are sometimes called basins or minima, correlate to more stable low energy system configurations. Meanwhile, peaks or barriers correspond to unstable high energy configurations. So here we have two neighboring minima labeled well A and well B, shown with their associated configurations. So keep in mind in these diagrams and those to follow, only 5 particles are drawn for simplicity, but you can imagine the remaining black area of the diagrams contain other particles forming a jam system. Okay, so when comparing the associated configurations of two neighboring minima, such as A and B, if most of the corresponding particle positions are only slightly different, then we have a global deformation going between the configurations. So here you can see the white and dash pink configurations don't perfectly overlap. So all the particles have changed position going from one configuration to another. Now in that Gardner phase I mentioned, it's actually characterized by these types of deformations, which are also sometimes called excitations. If there are large distances between only a small number of corresponding particles of two configurations, then we have a local deformation. Comparing the overlap of configurations A and B, all of the particles overlap except for the top ones, which are separated by a pretty large distance with no overlap at all. So in 2017, Scalier et al. Found energy landscape subbasins of thermal simulated glass particle systems actually correspond to highly localized deformations. This finding was in sharp contrast to the mean field prediction, which suggests that excitations should involve system-wide correlations, i.e. global deformations. So basically the mean field prediction suggests that the Gardner phase might be universal amongst amorphous materials, while Scalier's findings suggest otherwise. Since then, PhD candidate Cam Dennis and Dr. Eric Corwin here at the U of O found the jamming energy landscape to be ultrametric for athermal simulated particle systems, which essentially just suggests that energy minima should be related by global deformations. So as such, I set out to analyze the configurations of the athermal data that was collected by them. So my research question was pretty simple. In a jammed 3-dimensional and athermal simulated particle system, do the configurations associated with nearby energy wells differ by local deformations as was observed by Scalier, or will we see global deformations as suggested by the mean field prediction? And understanding configurational differences is significant because it'll tell us if the global deformations predicted by the mean field theory in the limit of infinite dimensions holds, in lower dimensions, such as these 3D systems. And so if this prediction holds, then the Gardner phase could be universal amongst amorphous materials, which can lead to the development of advanced new materials. For example, take iron. It's useful and it's strong, but defects in its crystal structure allow oxygen access, which results in rust. Meanwhile, glass is uniformly disordered, so there are no discontinuities in the structure that can cause such weaknesses. So by finding ways to make glass out of certain materials or with new molecular connections, we can potentially discover new, stronger materials. So before I jump into my project, I just wanted to briefly summarize where the data I analyzed came from. In brief, a packing or particle system was generated with n particles in a 3-dimensional cube. Minimizations were carried out until the maximum unbalanced force on any particle was below a threshold of 10 to the minus 20, and that's in natural units. Packings were minimized and their packing fractions decreased in a way to give pressures of 10 to the minus 1 going all the way down to 10 to the minus 6. And the packings produced at pressures of 10 to the minus 1, to the minus 2, and so on until 10 to the minus 6, those were taken to be the original minima. So those original minima were then perturbed and re-minimized repeatedly until 500 total distinct neighboring minima were recorded. And these perturbations essentially just move the particles some random distance in some random direction. And so all the configuration particle positions were saved, and this entire process was repeated for hundreds of distinct minimized packings containing 64, 256, 1024, and 4096 particles. So my approach to answer my research question was to find the Cartesian distances between corresponding particles of every possible minima pairing out of the 500 total neighboring minima associated with the given system. And then I'd use those distances to calculate both the root mean squared distances between minima pairings as well as their inverse participation ratios, which is I'll abbreviate as IPR from here on out. Then I would plot those IPRs against the corresponding configurational distances for analysis. And I'll talk more about the inverse participation ratio soon, but just know it's a good indicator of how many particles move going from one configuration to another. And that makes it a good tool, a qualitative tool to decide if local or global deformations occur when comparing configurations of neighboring minima. Okay, so some assumptions that were made is that radlers can be ignored. Radlers are just unstable particles that make no contacts to other system particles. So it's thought we can just completely remove them with no major consequences. So if the red particles in the diagram signify radlers, then neither of these particles, 3 or 5, will be included when we calculate the distances between the corresponding particles. And we also just assume that the periodic boundary conditions are not a problem. And what I mean by periodic boundary conditions, it's basically just like Pac-Man's world. So you can think of this 2D unit cell example as a system that's being mapped onto a torus or like a donut shape. So like the pink checkered particles that are in the 4 corners of the unit cell, they're actually, they're all the same particle. So it kind of like wraps back onto itself. So to get the displacements between the minima configurations, we first need to account for global drift, which can result from those, the perturbation process that I talked about previously. And that occurs when the unit cell has shifted. And it can be misleading because it can appear like you have a global deformation, but in reality, this purple and red outlined unit cells they're actually the same configuration. So to account for the global drift, we just subtract the X, Y, and Z positions of the corresponding particles of 2 configurations A and B to get these cyan colored displacement vectors. Then we get the mean displacement of corresponding particles in each direction. And the blue vectors show the mean displacement of the configuration B particles from those of A. Subtracting these mean displacement vectors from the configuration B particles yields a new configuration, which is shown in purple. And that's our new configuration B. So finally, the Pythagorean theorem can be used to get the distances between the configuration A and new configuration B particle positions. The diagram here shows these distances as just little pink lines. So the distance between the configurations A and B is then just the root mean square distance between the two, which is given by this second equation here. So using the particle distances, the inverse participation ratio can be calculated. So the IPR tells us how many particles moved or participated in going from one configuration to another. So in a system of n particles, an IPR of 1 means that one particle moved, which indicates a local deformation. An IPR of 1 over n means that all n particles moved and in a n particle system, so you would have a global deformation. So as another example, if you have a 1,000 particle system, an IPR of 1 over 900 would imply 900 particles moved. So you'd think it would be a global deformation. But if we kept increasing the number of particles in the system and we continued to see an IPR of 1 over 900, then we would have what's called a local deformation. So for that reason, I wanted to analyze several system sizes for this project. Okay, so I'm still in the process of getting all my data plotted. So today I'll just show data for 4 different system sizes at 2 different pressures. So we have a log-log plot with the IPRs on the y-axis and the RMS configuration distances on the x-axis. So just as an example, recall that all the blue data points correspond to a single original minimum packing that consists of 4,096 particles at a pressure of 10 to the minus 1. And from that original configuration of particles, a total of 500 neighboring configurations or minima were found. And then the IPRs and RMS distances between every possible minima pairing out of those 500 were calculated and plotted. So, okay, so notice how there aren't very many data points approaching 10 to the 0th power or 1 in the y direction. So, and recall that an IPR of 1 would indicate a local deformation. The highest concentration of data points have much lower y values, indicating smaller IPRs, i.e. global deformations. You may have also noticed that as the system sizes increase, the corresponding data sets shift downward and to the left, indicating decreasing IPRs and distances. And if you notice the general negative slope of each of the data sets, you realize that the larger distances between minima pairs have lower IPR values, where a small IPR, again, is a global deformation. Meanwhile, there is a trend for smaller configuration distances to be associated with larger IPR values. So overall, based off just this one plot, the neighboring minima appear to be correlated via global deformations. Now, at the low pressure of 10 to the minus 6, critical jamming is reached. So going lower in pressure would result in a system that is no longer jammed. So, our box of marbles, if we shook it, you could hear some rattling. So we still have the same trend of decreasing IPR and distance values with increasing system size. But there's a definite increase in the number of minima pairings with IPRs that approach 1. So at critical jamming, it would appear that local deformations could be more common. However, the overall trend of the data would still suggest that global deformations are dominating in the differences between the nearby minima. The shape of the data is somewhat different than in the high pressure case. So in each case, or in each data set, there appears to be at least 2 main peaks, where there was really only one obvious peak for each data set at the higher pressure. So here I just wanted to show a direct comparison of the high and low pressure data for the 256 and 1024 particle systems. If you move the white data behind the blue data like this, if I just toggle back and forth, you can kind of see how they overlap. But you can see that the single branch that you see in the high pressure data, so in white here. It still exists in the low pressure data, which is shown in blue, but there's a much stronger concentration of data points in the other peaks we see in the blue low pressure data. So I haven't had much time to really think about the shape of this data or what it means, but it's come up in all of my low pressure plots so far. So I'm thinking it might be like a universal shape that the data tends to collapse into. I'm going to try to plot these data sets again, but next time I'm going to try to color any of the data points that are calculated using the original minima packing in a different color, so I can see exactly where they turn up on these plots and which peaks. And in general, I just want to figure out if there's a higher incidence of any particular minima packings associated with the data points that form those peaks. But yeah, so basically, preliminary results suggest neighboring minima are related by global deformations, as my mean field theory would have us expect. If I can confirm this over the next few weeks, then that means the Gardner phase might be universal among amorphous materials in general. And there may be this kind of universal shape to these plots, but I won't know for sure until I've taken a look at what my data is doing on a larger scale. So so I finally got all my calculations run, but I still have about 11,000-ish data sets that I need to plot out by size and pressure, system size and pressure. So once my plots are completed, I'll be able to officially confirm if my hypothesis was right or not. But I'm also just really hoping I'll find some interesting new patterns that'll pop up that could take this research maybe an interesting new direction. Okay, and I would just like to thank the McNair Scholars Program for funding this research. And I'd like to acknowledge that the data I was analyzing was originally produced from research funded by the NSF Career Grant and Simons Foundation. And then another special thanks goes out to the members of the Corbin Lab. In particular, I would like to thank Dr. Eric Corbin and PhD candidate Cam Dennis for being so patient with me. All right, and that is the gist of it. All right, any questions?
Okay, do we have any questions for Nicole? Please feel free to enter them into the Q&A. You should see a Q&A section down at the bottom. I can't see your pictures, so raising your hand is probably not going to work. I have a question, Nicole. You talked about an initial pressure of 10 to the -1, and I was trying to conceptualize what pressure was in this case with little glass particles in boxes and things.
I know, it's very
How should I think about that?
I'm sorry, go ahead.
How should I think about that?
So it's a whole bunch of code that I'm still learning and getting acquainted with. But basically you have like this packing fraction, which kind of gives, it basically sets like the volume of the like the particle volume to the volume of the box. And as we like change that, it kind of changes. Well, that's such a hard question to answer. Gosh, I would honestly kind of need to go back through the code to like really give you a solid answer there. I'm sorry.
That's quite all right.
But it is kind of hard to think about. Like I had almost no coding experience when I started this project. And so it's a very long and frustrating process of like writing scripts and things. But yeah, I don't know. I've learned a lot though. It's been good.
So Noah, Rachel, or Nicole, do you have any questions of one another in terms of your talks? And give you an opportunity to ask questions. If so, just simply unmute and ask questions. But if not, that's fine too.
Nicole, before we do that, would you mind stop sharing your screen so that
Oh,
way.
I'm sorry.
There we are.
That's totally fine. Thank you.
Okay, I'm not hearing any questions. So I know that this is being recorded, and I'm hoping that other undergraduates and other people will simply, look at this in the recorded version later on. And so I generated some questions that I'm going to ask for them, whoever they may be, future audiences. And they're sort of general. I think probably, freshmen and sophomores who are getting started in the sciences would really appreciate hearing from you all. How did you get involved in your research? What did you do to kind of get going on that? If you wouldn't mind just saying a few words about that, I'd appreciate it. Don't be shy. Rachel, thank you.
So for me, I looked up online, that very question, how do you get involved in research? And they were just like, contact professors, do well in class, go to office hours. And so really for me was just getting over the hump of actually reaching out and not being, still being afraid to, but worst comes to worst, they just say no. And if they don't respond, wait a few days or a week later, likely a week later, and just follow up on your question because they're obviously really busy, and don't take that as necessarily a passive aggressive no. Be what's the word? Tenacious.
Sure. Noah or Nicole, you have anything else to add? Noah.
Yeah, it's kind of same thing of just I met Professor Palos through the North Star program, actually. And after the program was over, I just contacted him and just I kept it's just keep reaching out and showing interest, I feel like is the key thing.
Mm-hmm. Nicole, how did you get connected to the Corman group?
Oh, okay. Well, yeah, I just, I had done research in a physical chemistry lab, but doing that research, I realized, okay, I don't want to be a pharmacist. I'm going to be bored and I'm going to hate it. I have to do something with research because I just really liked it. So I had kind of eventually made more of a transition into physics, away from chemistry by then. And so I decided, with the pandemic, I couldn't physically go into my lab anyway to do measurements and whatever. So I just decided I'll ask Eric Corwin if I could do some kind of computational project with his group, because I kind of looked into his work. It was kind of interesting, and so yeah, I just went for it. I don't know. I just needed to explore a new field, try something out, and I just asked him, and he was like, "Yeah, sure. Start showing up to group meeting." I'm like, "Okay." It was really just that easy. So yeah.
So I'm hearing kind of a couple messages collectively between you all, which is to be persistent and maybe not take the initial lack of responses as meaning it, as much, not reading into maybe an initial lack of response, any kind of negative view, but rather than just recognizing that faculty are busy and it takes a couple of dings, as it were, to get their attention and proceed forward from there. But there's a third thing that research has shown is important, and colloquially it's known as imposter syndrome. And that might be the situation where you say to yourself, gee, am I really a physicist or a chemist? And gee, can I really do this? And I think, Rachel, you spoke just very briefly about that. And I'm curious if you felt at some point, and this may even go back to before research, this may be just simply when you came to the U of O and started in the sciences, did you feel at some time like you were an imposter? And if so, how did you work with that? How did you get past that? I know it's a little bit of an out there question, but I ask those kinds of things.
No, that's a good question. It's something that I still deal with, but you kind of have to look at the statistics of the work that you've done and so yeah, I came into University of Oregon just like as a non-traditional student, not really like, I didn't do very well in high school, and yeah, definitely questioned whether or not I should be asking a professor to join their research group. Thankfully, I have gotten good grades in college, but even if you haven't, I mean, there's been some effort. I mean, research skills don't necessarily translate over to like test scores. So, yeah, all that being said, this is still something that I am trying to learn how to deal with in my head, but essentially just like, don't let it take over and you just got to keep going. Yeah.
Thank you for that, Rachel. Anyone else? Noah or Nicole?
Yeah, it's kind of like, I don't know, I always kind of feel like when, especially when I'm in group meetings with like all of the grad students and professors, I feel like, what the hell am I doing here? But then it's when you talk to like a friend that's not in the group and you just explain just some tiny part of your research. It's when you're doing that and you'd be like, oh, I actually kind of understand this, and this is making sense, and it's not basic. Like this is actually complex stuff. So
Too, by having to explain it to others in some sense, maybe you were explaining it to yourself as you go along too, which is always
yeah,
helpful.
exactly.
Nicole, have you had any issues with this? If you don't mind sharing.
Oh no, I don't know. I have no experience with imposter syndrome at all. I'm kidding, obviously. Yeah, it's a problem. And I've asked professors about it. I'm like, how did you get over it? And they're like, it doesn't ever really go away. You just kind of learn to manage it a little better, but it's still there. But yeah, it's definitely something that just comes up a lot. But I don't know. I try to just use that to like push myself harder, I guess. You know, if I'm worried about being an imposter, then I should try to really be on top of my stuff and know what I'm doing. And in a way, it can be motivating. But you know, obviously I'd rather not have to deal with it at all. But you know, it's something that's there, and I think most people like, you know, deal with it. But at the end of the day, you just got to be positive and just remind yourself of your, you know, your smart moments throughout the day, right? Don't, you know, get too caught up on like a bad test score or a bad grade or whatever. Because it's like what Rachel was saying, you know, research skills and like test scores don't exactly match up all the time. So
Sure.
just like, yeah. So pretty much the same to everything they said. Yeah.
Thank you. I just have to say that I'm a ancient dinosaur professor, or maybe I look like it. I really am. And I still have imposter syndrome sometimes, so it doesn't go away. I really appreciate your noting that and sharing your strategies for dealing with that. Another quick question. I don't know if any of you saw Tamara Maciel's keynote talk on Monday. I knew Tamara when she was in physics, and she mentioned having, feeling like an imposter when she first started off as well sometimes. She went and did a lot of outreach. We worked at the Science Factory. I think it's got a different name now. She rekindled the SPS, Society of Physics Students and things like that. Have you guys done anything like that? And does that help? I'll point out, Noah, that you mentioned talking to a friend who wasn't involved sort of helped you feel better. And so in some sense, I guess that's what you'd call social persuasion. Any thoughts about that? You're my guinea pigs, by the way. I hope you don't mind. Okay, let's move on. Last question. I wanted to ask you about particular skills that you find you really need to use in your research. And, if any of those were surprises to you when you got into your research. Could you name a couple of particular skills that you find very useful in undertaking your research, and give any background you feel like giving? None, that's fine. And also, were any of those a surprise to you? I can guess one skill right off the bat, but I'm not going to put it in your mouth. I'm not going to say it. We'll let you guys say it.
Programming, I'm assuming, is one of the skills.
Yeah.
Wasn't too surprising, but the amount programming was used was kind of surprising for physics research.
Yeah, you all three obviously been using a lot of, I'm going to guess Python generally, right? Python packages and that kind of thing. Any other kinds of skills that stand out for you?
I mean, I don't know if this is like a skill, but it's something that I know I need to work on. Is just knowing when to like stop and ask for help, instead of like continuing to struggle with something. So I don't know. Not really a skill, but like that is something that surprised me doing research. Is just like how often I would like find myself like I'm just kind of hard-headed. Like I don't like to ask people for help. And so I learned really quickly, like, no, I need to like know when to break down and ask someone for help. Yeah.
Yeah, I experienced a similar. I would be really stubborn and.
Questions and.
I think you're at least cutting out for me, Dean.
Did we lose Dean? I think we did. Well, if you still want to add any more skills, I'm happy to continue to facilitate at least the space till he maybe comes back. Any other skills that you've needed to develop and or need for research?
I was just going to like emphasize what Nicole said. It's really easy. It was really easy for me to get stuck on something and just like stay up really late when I shouldn't have, and keep trying to solve it when I could have just waited till the next day asked, and that would have taken like a couple minutes, or maybe not a couple minutes, but not like hours. And also, I guess, reading papers that you know absolutely nothing about, and being comfortable with just like working through all of the jargon, as well as the physical concepts. Also don't know if that's a skill, but definitely been improving that during research.
Thank you for carrying on while my country internet out here killed me and dumped me out of Zoom. So I'm back. I missed some of your answers, but I can look at the recording and listen to it as well. So I think maybe I better get out because I just barely have a connection here. So I'd like to thank you all for really wonderful talks. Really appreciate it. And I appreciate your candid comments at the end to my pokey questions. And I'm glad to see you guys are all doing well. Right? Very different topics, very interesting. Keep up the good work. Thank you so much for your presentations.
Yeah, so we're all good. Everybody can.
Thanks, everyone.
Thank you.
Yeah, thanks.
Did people hear what I just said? Just sorry, my internet's bad out here, out in Crow.
No worries. Well, thank you all. Have a good evening. I'm going to end the meeting now. Have a good rest of your term.
Yeah, and thank you so much for your wonderful talks. Appreciate it very much. Nice to get to know you.